Assalamu alaikum and good morning everyone. Welcome to day 4 of the course Nanoscience and Nanotechnology.
Assalamu alaikum.
Assalamu alaikum sir.
Walaikum salam, sir.
Did you see the slides?
Yes sir.
Good. Let's start because we have too much slide today. Good morning, everybody. What's the time now in Pakistan?
11:05 sir.
AM or BM?
Yes sir. AM.
AM. Yeah, then good morning is correct. Okay. Today we are gonna talk about the class characterizations of nanomaterials. When you prepare any nanomaterials, you have to prove that is nanomaterials. It's not. I told you yesterday. Even if you prepared uh, um, one nanomaterial reported means you just follow the procedure of synthesis. You have to confirm and elucidate that is nanomaterial with specific dimensions. And if you're preparing for the first times, you have also to confirm because otherwise you cannot publish because you are not alone in the world. Okay, so I will just show you some the main characteristic tools utilized for the characterizations of nanomaterials. Actually, if you are preparing some one of the nanomaterial without these characterizations, your work is incomplete. But if you did these characterizations, that now your work can be published. But except one of this, you are under the risk. But there are others tools you can use, but this is option based on you. If you use and characterize and you confirm, then you will go for high impact factor journals because yeah, this is you will go for higher because you will interpret and give more explanations and interpret the mechanism and so on. So this one, morphological characterization using scanning electron microscope, transmission electron microscope, and the energy dispersive X-ray, which is unit equipped to transmissions and equipped to scanning. Okay, and the chemical structure using Fourier transform infrared spectroscopy, which we called FTR, and this is everywhere, and crystalline structure called X-ray diffractions, and the chemical structures for carbon-based nanomaterial, and it's called Raman spectroscopy, and it's very, very important. Ultraviolet visible spectroscopy, then dynamic light scattering for nanoparticles, analyzer solutions means when you go for biological applications, you have to use it because it's gives informations about the colloidal stability of nanoparticles. Because I told you before, if you are going to prepare one inorganic nanomaterials for biological application, at least you need stability 3 days, at least 72 hours. So you have to measure using dynamic light scattering because when you measure the TM, you cannot see the hydration layer and the polymer surrounded to the nanoparticle. You only see the nanoparticles, okay? And in this case, nanoparticles is could be like 30 or 20 nanometers. But when you see in DLS, it will be 50 or sometimes 80 or 100 because the laser will see only the hydration layers, okay? Then finally, a specific surface area for the nanoporous material. So let's start with first of all, scanning electron microscope. I told you the nanomaterial exists long time ago, in 3,000 years or 3 million years, nanomaterial is there, but the problem is the people don't know is this nanomaterial or not. And even the synthesis procedure of nanomaterial was used a long time ago, but nobody knows because there's no any high resolutions or high magnifications instrument to see because the resolution equal zero point 0.2 millimeters, and the people use the microscope, optical microscope, and that's all 1,000 times more. But when the people discovered the electron microscope, the resolution become more than 500,000 times. Then now you can see the like you heard a long time ago about femtosecond, right? Which discovered by Professor Ahmed Zwiel, Egyptian American scientist, and he got a Nobel Prize in 1999. Actually, femtosecond is exist like picosecond now is exist is a time exist, but what he did, he just discovered the camera which recording this time. Okay, but the time is exist even after 50 seconds. There's a picosecond and still also exist, but we cannot see, we cannot record the time. But he what he did is he just using laser, he just discovered and fabricate camera recording this time. Recording this time is very important. What is the main idea of the scanning electroscope microscope and how it works? It's very simple actually. You have electron beam, and the electron beam is gone to the anode, and then electromagnetic length coherent that length. Then finally you have some beam, and the beam make scanning to the samples, and then collected, remove after putting the material, after scanning the material. There's some rays will be reflected, like secondary electrons, X-ray electrons. I will show you here. You just incoming electrons, incoming beam. After the beam comes, it makes scanning to the sample surface, and the depth only of the sample in under investigation is only 10 nanometer on the surface. 10 nanometers on the surface of the material. Okay, then after that you will see there is some backscattered electrons, the secondary electrons, the X-ray electrons, and all the also cathode luminescence electrons. All these electrons will be collected by detectors, and then going to image development unit, and then giving the image of the materials. Like here, you can see here electron beam release electrons, electron gun, I mean electrons, then accelerated up to high to dozen of energy. Then the Fox beam makes scanning to the material surface. Then finally develop detectors detect the secondary electrons, the backscattered signals, and the X-ray. Then go to image development, which is giving the current image of the materials. So what is the precautions for the electron microscope? Actually, the electron microscope is big instrument. We will show you I think you see the image of this instrument. It needs a big room actually, and the room it should be conditioning, and under the measurement there should be vacuum. So all the pressures inside the chamber of the instrument should be very, very, very low, to don't disturb the electron beams, and the sample should be clean, should be also, if the sample is not conducting, the sample should be conducted. Otherwise, it will not there will no interactions between the electron beam and the samples. So if the sample is not conductive, then we should coat with the gold or platinum. And that's why there is a simple instrument besides this SEM, is called coating machine. That coating machine, you put the samples, and it coat your samples with very thin conducting film. Usually it comes from gold or platinum. It depends or sometimes carbon. It depends on the coating machine facility in your lab, but mainly gold and platinum to make the surface conductive. That's why you can see high resolution image. If there is no coating, then your image will be not good. That's why I recommend you, when you go to measure scanning electron microscope, go for high field emissions and go for the machine which have a coating machine, because sometimes if you are not working in non-conducting, then what's the solution? Your sample will be not good. Okay, and then finally nobody will distinguish your nanomaterial if you have nanomaterial, for example. This is the scanning electron microscope can characterize or can investigate or can examine feature fractures, surface, and electronic device, fiber, coating, particles, all of this kind of. You see the slides or not?
Yes, sir, we can see.
Okay. So usually, actually, when use scanning a scanning electroscope is used only one the powder sample. It's not solution sample. So if you have a solution sample and you want to measure a scanning electroscope because you don't have TM, then you have to make a film. Listen carefully. If you are making colloidal solutions and the colloidal solution containing some gold or graphene, blah blah blah, any materials, and the only you have in your town is scanning or university is scanning electron microscope. You don't have transmission electron microscope. Then in this particular case, you have to make a film in glass light from this colloidal solution, dried, and go to the operator measure. Okay, some examples. This is, some high resolutions scanning electron microscope image of some nanomaterials. Uh, Picture, sorry, picture A is some zero-dimension nanoparticles. It's inorganic nanoparticles, and I think this is uh, film, and see the high resolution image. This means this instrument high field emissions, and the other one is graphene 2D material. The number C is nanowood, one dimension, gold nanowood. Then number D is polyethylene oxide, nanofiber, and this is actually prepared by electrospinning machine. Then the number E is zinc oxide nanowire. Okay, and the number F is tungsten oxide nanowire network 3D. Number E and the number F is 3D nanomaterials. So this is, yes, this is very good image actually. Means this instrument is very interesting and is very good. That's why. Actually, the scanning electron can be used to measure the cross section of the film if you have a cross sections, and also it can be used for measuring as macro scale. I mean, starting from the macro scale to nanoscale. So if you have some insects or you have some biological samples or whatever you have, it can measure. It can be easier. You can do cross section and see the thickness of the materials. It's very easier. It depends on what you have in your mind and the operator skills. But the instrument can do many things. The instrument can do many things. But it depends on you and what you know what you have, and the operator. Because if the operator is not good and the operator is not clever, then he will not do anything and he will spoil your sample. And this is very important because this kind of instruments, they need the operator to have a training and update the training every couple of months or something. So, but you can do cross section if you have a coating, you have a film or something. You can just make scratch and he put it in the edge of the sample holder and measure it. It's very simple. But I told you it need clever operator. So what is the advantage of the scanning electron microscope? Yeah, electron microscope have a variety of number of scientific industry service. You can help old electronic. Even I yesterday I told you about the laser applications and some other technique, lithography and so on. So they used the scanning electron microscope as a quality control unit to see what they did is nano or not, and what is the surface of the material, because for electronic applications, the surface of the electrode is very, very important. So it used the quality control for the electronic applications. So any electronic factory have some scanning electron microscope to see the surface well, at see the topography and the morphology, and also it can be used for morphological compositional detect, analyze surface fractures, provide information about microstructures. It can be used for different fields, actual life science, biology, medical, forensic science, metallurgy. Yes, there's a many applications you can use, but the problem is, yeah, nothing is complete. We always have a we if we have a thing, we have anything good, then we have some side effect. Like any person of you, all of you, including me, we have a positive habits and the negative habits. We have a merits and demerit. We have advantage and the advantage. But when my advantage become much more than my disadvantage, then I'm good man, and the people would say he is good man. And also, if any one of you have the number of merits he have is more, then we say he's good man. But anyway, he have a disadvantage. Disadvantage is the instrument is very, very expensive, very, very expensive. So I think now the good one maybe cost around $0.5 million. $0.5 million. The good one. And the maintenance, actually, it need first of all, it need a big room, and the big room should be conditioning 24 hours during the instrument is working, and the operator should be have special training required to understand many things, and also update the training, and also the preparation of sample. It needs a coating, and sometimes you don't have the coating machine, then the sample will not be good. And this instrument have some magnetic item inside, so it gives some radiations, especially to the operator. For you, if you are going for say 2, 3, or 4 samples you are measuring, then no problem. But for the operator, it will be negative effect later. Uh, the other issue is this scanning electron microscope is only restricted to solid state sample. Liquid sample, no. Liquid sample, you have to make first drying, or you have to make coating. It depends on you, but it's only restricted to solid state samples. Okay. Yeah, I told you about the risk radiation exposures, and this is, also is very important. Slide number 13 now. Did you see?
Yes, sir.
Okay. The other instrument is a transmission electron microscope, and this is the other face of the coin, because we have a coin. The first face of the coin is scanning electron microscope. This is transmission electron microscope. Same phenomena. Everything is same. But the problem here, the detectors will be in the bottom of the sample in this case. So the electron beam will come and penetrate the sample, and will be collected. The beam in the bottom of the samples. Okay, that's why your sample should not be more than 100 nanometer thickness. If your sample is more than 100 nanometers, then the image will not be good, because will be risk for unpenetrating of the beam. Okay. So here, electron beam is forming on the tip of the heat filament, and it's going up. Then this is, for example, in the sample, if you see the Olympic as a picture, the sample is the green one. Then the detectors will be in the bottom of the sample, collecting all the electrons, and then the image will be monitored, and the image development will make the image of the samples. Here's the examples actually and how it works. Actually, the electron beams come penetrating the sample. That's why the specimen thickness should not be more than 100 nanometer or thinner even sometimes, because and also in these materials or in this instrument, you have you have to use some sample holder, which we called grade, TM grade. And TM grade is two types. It depends on your type of materials. Look, this is maybe not working in your country, because in my country there's only we have only carbon grade, but this is not good, because when you have a two-dimension nanomaterial and one-dimension nanomaterials, or even three-dimension nanomaterial, we have to use wholly carbon grade. Then it will be like network. And when you put the one dimension or two dimension material, it will be hanging. Then it will be clear in the pictures. But the problem is because we cannot get this one, so we have only and the carbon carbon only grade is only for the ZOD, which is nanoparticles, because nanoparticle will not be suitable for the holy carbon. Okay, but I think in your country you have only carbon only grade. This is to make a high resolution. I mean, to show the sample in good way. Okay, because we are doing that one to clarify and elucidate and to give a clear evidence to the reader and to the reviewer and to the investigator that you develop that such kind of nanomaterial with such kind of specific thickness and dimension. Okay, so it's better to show it in better way. So here you can see all the grade. I told you it's around 3 millimeters, and you should prepare your sample. First of all, if your sample is solid, then you have to dissolve in some water and make ultrasonication, because any nanomaterial you have prepared in solid state, it will be in aggregated form. When anybody of you even order some titanium dioxide nanoparticle or platinum or prepared, he will see powder, right? But nano, you cannot see by your eyes. So did you ask yourself these questions? Whenever any prepared nanomaterial, you filtrate it and you get some powder and you see the particle size, right? So how did you? Why did ask yourself how I prepared nano, but I can't see by my eyes? Then it's not nano. Yeah, it's aggregated form. Then you have to individualize using ultrasonication. Then, then you have to disperse using micropipette on the surface of the grate. Then you have to dry, complete dry, complete dry, complete dry. This is very, very important. There is a junk and the stupid TM operator everywhere. They spoil the instrument in 1 or 2 months because they didn't complete dry. Just once you go to give you a sample, you are just put in the sonication bath, and after 2 minutes, he just get from back of it and put in the grate 1 minute, and then insert in the side in the instrument. Then when they exposure to the beam evaporate the solvent, and most of the material have even alkaline or acidic natures. Then it will go to the filament, and after 1 or 2 months, it will corrode the filament. Then the instrument will be broken, waiting the maintenance after 1 or 2 months, paying money, and again this sequence. So each TM instrument is working only at least 3 or 4 months working and 3 or 4 months not working, need maintenance, because the operator is a stupid and he don't know what to do. When I was working in as a PhD student in South Korea, if my sample is hydrated, still have some moisture, all the lab member will be prohibited to use the instrument for 1 month, because they care much and they know what they have and they know what the facility have and they learn much. But in our country here, no. I tried to explain many times. And even when you just, if your sample is hydrated, it will not be good and it will be dense under the beam. So you cannot get a good resolution even for you. If you are not honest and you don't care about the instrument because you are paying money, if your sample is much hydrated, you cannot get good image. You cannot get, and even when you see under the TM microscope, you will see your sample is dancing inside the beam. Okay, so your sample should be complete dry, should be complete dehydrated. Hydrated sample will not be good even for you. So in my case, when I go to measure TM, I go by myself, with my student. I will not trust the student to do that, and I ask the operator. I prepare the sample. I put my sample in the tip by myself, and I put it in the oven for at least from 15 to 20 minutes to complete dry. Then I do it. That's why my TM sample always is good. Okay, so this is very important. This is very very important because you are paying money, and you are giving some message. Sometimes you are preparing some very very interesting material, but you didn't elucidate it well, or you used some not good instrument or some not good tools. Then it's nothing. The net is zero. Okay. Yeah, advantage of the TIM, yeah, is good, and the high resolution is giving it's giving information about the surface and shape and size, clear clear image information about the size and the dimension and everything. Uh, but only for this advantage, it only limited to the liquid state samples. In your sample have to be dispersed, and the instrument is very very expensive, very very expensive. Is 1.5 more than scanning electron microscope. So if you want to buy good one now, then I think at least you need point 0.6 or $0.7 million to buy it. The good one, I mean. You need also, the operator should have special training and upgrade. But also there is the image only black or white. It's not it's not confocal microscope or bio FM or something. Not like FM. The image is colored. Here is black and white only. It's not like FM, atomic force microscope. Uh, yeah, in this case actually different than the CM. Here you need some precautions for the preparation of the samples because you need a grade, and sometimes there's shortage in the grade. In my case I want to measure TM 2 months ago, but before it actually, but the problem is because there's no grade, so I could not measure till now. So this is one of the problem. There's some special sample preparations, and they need some special sample holder which is called grade, and the grade is not available, and it should be uh, uh, imported from somewhere. And the instrument definitely is expensive and need a big area conditioning and so on. I will just show you some examples of the TM I showed you yesterday, so I don't need to do one more again. This is, you see slide number 19?
Yes, sir.
Okay,
Yes, sir.
okay, okay. You see number 20?
No, sir, 19.
19.
Yes, 19, sir.
Okay, okay. Now you see 20, right?
Yes, yes.
Okay.
Yes, sir.
This is image of one dimension nanomaterial using transmission electron microscope, and this is 2 dimension actually. This is 3 dimensions of the nanomaterials. The other one is is EDX, or energy is dispersive X-ray. So this is one equipment actually connected to the TM or CM, and this is responsible for measuring the elemental composition of the materials. Um After you measuring the TM, SEM or TEM, you need to know the composition of the materials, right? So this instrument, this unit is analytical technique used for elemental analysis of the samples, and it release interactions of some source of X-ray existing with the samples and give the different except hydrogen, and give all the element carbon, oxygen, nitrogen, whatever you have. They will give you have two options. Even you can select area, like in picture A, you can select the area and you can analyze this area, and you give all the composition of this area, or you just make a mapping to the some also selected area mapping. Then you can give a color like this, and they will give all the element with different color, and they give the percentage. Yes, this is very important actually, but this is not accurate. XBS is more, X-ray photoelectron spectroscopy is more accurate than EDX, but it's also important. This one is important because sometimes you cannot find is XBS in your country even, or your city, because in our case we have only two copy of XBS. Only one is working and one's not working in all the country. Can you imagine? So, but EDX is available everywhere, so it's okay. They will give you a chart like this one, giving you the element and the level which exists in the element also. Uh, yeah, the other one is X-ray diffractions actually. This other instrument actually, instrument number three. When you prepared any inorganic nanomaterial, is only X-ray diffractions or X-ray tools is mainly used to characterize the crystalline nanomaterial, and of course, all all the inorganic nanoparticles, the inorganic nanotubes uh, is crystalline materials. So whatever you prepare, silver nanoparticle, gold nanowood, iron oxide nanoparticle, nickel oxide nanoparticle, zinc oxide nanoparticle, titanium dioxide nanoparticles, um, halloysite nanotubes, titanium dioxide nanotubes, titanium dioxide whatever, any inorganic oxide or inorganic nanoparticles is crystalline, and they have specific characteristic XRD peaks. And this because it's crystalline, and the XRD is mainly characterize the undifferentiate between the amorphous and the crystalline. Okay. Yeah, it's non. First of all, it's non-destructive techniques. SEM and TM is destructive techniques. The sample you cannot get again, because in a scanning electron microscope you will coat the sample with some gold or platinum, so you will not use again. You need only 10 milligram or even less than 10 milligram. So it's not okay. It's not good. Yeah, it's useless anyway. And for TM, you need only 5 milligram or 1 milligram. Also, you have to disperse, then you have to put in the carbon grade, so you cannot get back again. It's called destructive techniques. But XRD is non-destructive techniques, means after you put your sample, you need at least zero point 0.5 gram to put in the groove of the sample holder, then you can get back again. No problem, no problem. Okay. It gives you the crystallography, graphical structures, the unit cell, the chemical composition, also the physical properties of the samples. It gives you much more information actually. Yeah, here I want to show you this one. It's better. I want to explain to you there is some things called crystalline size and the particle size. Any particle size you have, like titanium or nickel, it contains some crystal size. There's some crystal, means the material will be ordered in some uniform ordering. Like, did you see the picture number 29? Is the slide 29?
Yes, sir.
Okay, So there is a big difference between particle size containing amorphous, crystalline, and so on, and crystalline size. So in X, the XRD will measure the crystalline size and even the interlayer distance between these two. Here there's some line, right? And the distance between each line you will see, and they're called interlayer distance. And if you, for example, if you have a clay or have something, so sometimes some material will go inside. So this is very, very important actually. XRDs, yeah, generally you can interpret many things. If you have, for example, like if you have a metal organic framework, you have to interpret many things. But for the normal characterizations of the nanomaterial, there is a fixed characteristics pattern, XRD pattern for each materials. If this exists, then it's okay. And also, even you can know the particle size, diameter, but this theoretically using shear equations and the theta of the peaks. Then you can just compensate and you can see the average size. You can see the average size is 30 or 40, but this is not accurate. And I don't recommend. I don't recommend. I don't recommend to measure the particle size using XRD because it will not be accurate, first of all, and also it just theoretical. But it's, if you are going for high impact factor journals, or if you're going to really enrich the scientific society by your publications, it's better to go for TM. Yeah, this is just examples about the graph you get and the type of the material. You have amorphous material, like the material in the right side. It's amorphous. It's arranged in a regular form. Okay, and then you have a crystalline material, the last left one. The material, the atoms of the materials is arranged in a regular pattern, and their smallest volume called the unit cell, and this is repeated. Okay, and there is a polycrystalline, means the material is have a different unit cell or different dimension unit cell, and when you measure the XRD, the up graph number A is means which are created for amorphous. Amorphous means the material is not arranged in regular form, or not arranged in order form. But the top down number B is crystalline material, and each XRT patterns is means some HL form. I mean, this complicated actually. It need one lecture alone, because sometimes if you know some of crystallographic of the materials, you can simulate the XRD. You can simulate the XRD using some program. So that's why I'm saying it's big issue. It need at least one or two lecture only to explain that more details. But for you, at least you need XRD, because XRD just to put your sample, and after 20 or 30 minutes you will get the pattern, and this is pattern going exactly the same peaks for silver, then you have a silver, gold, then you have a gold, and so on. Yeah, there's a many things, the characteristics of the XRD. We need to go for this one, because I already say about this. The advantage also, I told you, the XRD is widely used for many things, and actually only 20 minutes you can get the result. Uh, Provides mineral deformation. Also, I no need to say. Yeah, this is a sample holder. I told you. This is a sample holder. There's grooves. Do you see slide number 33?
Yes, sir.
Okay, this is the sample holder you have to put. That's why I told you it needs at least zero point 0.5 gram, or at least 250 milligrams uh, to cover all the sample holder, and to give to put in the materials, and to get back the material again. No problem, because it's non-destructive techniques. This is the XRD pattern of different materials, and showing, and every pattern have characteristic unit cell, and you have to put. Sorry. This one you can see now. Some examples of the XRD, and also this is XRD and IR. Actually, the right one is XRD of some metal organic framework, and the left one, I mean, the right one is IR. We will talk about the IR now. Okay. FTR اللي هو Fourier transform infrared spectroscopy. Yeah, it's one technique is used for many materials. Anybody doing anything, anybody doing anything, even physics, chemistry, material science, engineering, he need to do FTR. FTR is one technique is reflecting the functional groups of the material what you have. Is qualitative techniques, is not quantitative. This means they only saying you have this functional group because these peaks will create it, and the peaks reflect based on the position of the range of the observed position of these peaks. That means we have a C double bond O, we have OH, we have a C double bond C, and so on. So this we have amide group. We have, so it gives you only some information, some qualitative informations about the existence of the functional groups of the material, but they doesn't mean they give the percentage. They only give qualitative, and this is very important. And that's why we say is a chemical structure of the material. That's why any person is doing any work, he had to do FTR for the blank and for the treated samples or the functionalized samples. Even if you are doing organic and functionalize something, then the new functional groups will showing in the FTR graph. Yeah, this is this is examples of the FTR of some textile material which treated with some different material, and you can see the blank, the cotton blank. Doesn't have some specific functional groups, and after coat with some other functional material, so new function will created, and you can see new peaks have been appeared. Actually, this means your process is successful. The other one is Raman spectroscopy. Raman spectroscopy is a fingerprint of carbon materials. Actually, it can be used for different material, but for carbon nanomaterial is a fingerprint. Yeah, I forgot something. Yeah, XRD also is one of the most important tool to characterize the graphene. One person will ask me, how is this, professor? Because the graphene sheet will have amorphous shape, but the graphite or graphene oxide will have a characteristic XRD pattern. So for graphite, will have as a very sharp characteristics XRD pattern at 226 theta angle, but graphene will be exfoliated, so graphene will be amorphous, and the graphene oxide will have at 22. Okay, 22. So that's why XRD is one of the tools utilized for the characterizations of conformation of the exfoliation of the graphene. Raman spectroscopy, I told you, is a powerful techniques. Raman spectroscopy is similar like FTR, but FTR is measuring the soft functional groups, but here is a solid functional groups. Okay, so it's very important because it measures the interaction of the samples with the electromagnetic radiations, and for carbon materials. Yeah, yeah, yeah. For Raman spectroscopy, the carbon materials, we use the Raman spectroscopy. If anybody of you working in carbon materials or carbon nanomaterial, and he didn't do Raman spectroscopy, then his work will not publish in good paper, and he will wasting his time, and he's not did good work. Even if he could be lucky and publish his work, he is not doing is not correct work. Okay, because Raman spectroscopy is a powerful technique to characterize the quality of the carbon materials and even to confirm what kind of nanomaterial what you have. For Raman spectroscopy, we use the flow to exfoliate and to confirm the exfoliation of the graphene, because any carbon material have a D band and G band. D band is responsible for the disorder in the carbon structure, and G band is responsible for the sp2 hybridization of the carbon structures. And the ratio between the G band and D band is reflecting or displaying or evaluating the quality of the graphene sheet or carbon material what we have. And for graphene have two D band and they have D and D band, D dash band also at 2950 and 2700 is 2D band. So if this band is exist, then you have a graphene. And for the carbon material, for nanoporous carbon material, the D band, the ratio between D band and G band reflecting the quality and the good graphitization of the carbon materials. So this is, saying, like, for example, when you have a D band and G band and the value is 0.76, this means it's not good. But when this value have been uh, decrease, this means you have a good samples. You have a better samples, and your activation doesn't harm much the materials. UV visible. I think this instrument you have it, and the phenomena when you see violet or you see blue. This means that you see the complementary color. I mean, like when you see the any material in orange, for example, this means this material is green actually. You are seeing the complementary. I think you know this in secondary school. So I will skip this kind of things because it's simple actually. Uh, yes. But what I want to know I want to tell you is most of the inorganic nanomaterial have a plasma resonance, like gold, silver, and some other materials, and even graphene also have some plasma resonance and some characteristic peaks. So if you have a UV in your lab, you can only by doing some simple experiment, you can know you have a gold or not, you have a silver or not, you have a nanomaterial or not. And also this is used for the measuring the concentrations for water treatment, and I think it's common to most of you by using Lambert's law. So I will skip this kind of things because it's yeah, it's it's common and it's basics. The other, yeah, sorry, because the times is coming much. Uh, the other things which I wanted to explain to you is dynamic light scattering and delays. I told you when you are target your materials for biological applications means you need to have a stable colloidal solution, because you prepared, for example, some uh, silver nanoparticles or gold nanoparticle or iron or nickel or whatever, and you wanna use it as an anti-cancers or whatever your application, but anyway, biological application, then you have to measure, you have to make colloidal solution and measure using DLS. DLS actually is measuring using the velocity of Brown motions, and it's kind of the hydrodynamic size. Actually, when you prepared in, for example, if you prepared silver nanoparticle, for example, and you used some polymer or plant extract as a capping and reducing agent, right? Then definitely, as we explained during the last 3 days, the capping agent will make a round shell around the silver nanoparticles. When we measure this one using TM, the TM will not see the polymer material. TM will see only the inorganic material, and the beam will penetrate only the inorganic material. Then you will see the exact size of silver, which could be 20 nanometer, for example. But when we measure using DLS, the laser ray will only measure the big particles. Means because you have silver nanoparticle is 20, and you have the polymer shell or the capping agent shell, which could be 10 or 20. And after that, you have a hydration layer from the solvent by hydrogen bonding. Okay, then it's like a hydrodynamic size. Then you will see, and the graph will be the size will be maybe 80 or 90 nanometers, and this is the actual size. Will go through the theorem because the theorem is hydrophilic, right? And you will use silver or gold as an anti-cancer. So you will inject in some solution to go inside your serum, right? So the motion will be this hydrodynamic particle size, not the one you use in the you see in the TM. So if you measure TM and you find your sample is 50 and you measure day less and the size is 150, 120, don't confuse. This is logic because you have a capping agent layer, then hydration layer. That's why we say it's a hydrodynamic size. Clear? This is clear or not? Somebody reply to me.
Yes, sir, it is clear.
Okay. And that's why the diameter here, it depends on the ionic surface, the surface structures, and the shape of the material. Okay. There are the three types of distributions. You have a volume size distributions. That's why I recommend you to use only, I will explain the three, but I recommend you to use a number. You have a volume size distributions. Okay. And you have a number size distribution and number volume. Yes. Yes. Volume. We have a volume size, number size, intensity size. But I will explain to you why I recommend you number, because suppose I give it to Jahid or Sajid or any one of you, okay, or Malika or some person. I gave him 5 apple, okay, or 10 apple, and in the meanwhile, I give her 1 watermelon. 1 watermelon is occupying big volume, right? But it's only one, and the 10 apple it occupying maybe 20 or 30% of the volume the watermelon occupy, right? So when you prepare any nanomaterial, the conversion rate will not be 100. Understood? So means if I start to prepare some silver nanoparticles or something, so maybe 80% become silver nanoparticles. And in this particular case, I have two categories of the size. One size is 5 nanometers, and this is maybe 100 particles. The size is 5 nanometers. And we have only 10 particle. The size is 100 nanometers. The 10 particle size is nothing. It's 10% regarding to the other, the 5 nanometers. But it will occupy big volume and big intensity. And it will give you fake results. But the majority of the nanoparticle you have developed, which is 100, the size is 5 nanometers. That's why if you use the volume distribution or intensity distributions, they will show you the 100 nanometer is the majority and the 5 is the minor. And this is not correct. We are dealing about how many particles we have. Then if you use the number distributions, they will show you the high number of particles. It depends on the size. So if, for example, you have 100, the size is 5 nanometers. Then it will give you big.
Excuse me,
Okay.
we are left with only 2 minutes in the class, and we will resume our class
Okay.
in a while.
We
So
will learn.
thank you for your
Because I have another meeting today, so we will finish in the time. Okay. So the last material, last
sure.
tools is a specific surface area, For the nanoporous material, I think the nanoporous material, for nobody, if anybody don't know, there is a two category. Even if based on the particle size, as the nanopore diameter, it could be microporous material if the pore size is less than 2 nanometers, and it could be mesoporous material if the pore size between 2 and 50 nanometers, and it could be called macroporous material if the pore size is more than 50 nanometers. And why we measure, yes, sorry, and how to measure this one? We using we measure the specific surface area of this material using BT analysis. BT analysis actually give you specific surface area, both size distributions, heat size, and everything. And in this case, we use inert gas. Is called argon or nitrogen, and they fill the pores with this gas. Then we measure the mass of this one, and we could know how the surface area during the volume of the gas absorbed in the material, but we have to make activation of the material using under vacuum to remove all the moistures. This is actually the main issue of the instrument. Actually, this instrument is called gas analyzer, or the apparatus actually. It's not expensive actually. It may be point 0.1 million dollars. It's not much expensive. And it depends on the absorption desorption, because the nitrogen will go inside the pores and fill. So when you fill all the pores, then you measure how is the math, or you know the math of the material, and you know the math of the gas, and based on the molar mass of the nitrogen, by some calculations, you know how is the surface area of the materials. And this is very important actually. Here, oh, and the shape of the material, and based on the monolayer. It's it's the instrument is automated actually. When you put your sample, they will give you the isotherm, and they will give you surface area and both size and everything. You don't need to do anything, but I'm just explaining to you about the phenomena and how to do and everything, and also based on the yeah this is very important actually. Based on the isotherm, you can know you have type 1, type 2, type 3, type 4. Type 1 is just iobate classification of nanomaterial. As I told you, you have a microporous, you have mesoporous, you have macroporous, and based on the hysteresis loops,